Um, Today we're going to continue working with those graphs. But we're going to talk about. So we also talked about how you either shift them up or down, or left or right. You can also flip them vertically or horizontally. And I'll remind you, this is going to be true today as well. If you do something to the outside of the graph, like here, where we're multiplying the outside by a number, that's going to affect the graph in a vertical way. On the other hand, if you do something to the inside of the graph, or I should say the inside of the function, like here, where we're multiplying by b before we do the function, we're multiplying b by x, not a by f of x. Doing something inside the function before you apply the function is going to affect the graph horizontally. And here's what happens with these particular things. So if you multiply on the outside by a number a, that's going to either stretch or compress the graph vertically. So if you multiply by a number that's larger than 1, you're essentially going to make all your y values bigger for each corresponding x value. So you're going to end up stretching the graph vertically away from the x-axis, both above and below, if you multiply by a number that's larger than 1. On the other hand, if you multiply by a number that's between 0 and 1, like 1/2, you're going to, the book people often say compress, I like to say squash. You're going to squash it down or smush it down vertically so that it's not as tall as it was before. And we'll definitely see some examples of that. I will also point out that if the coefficient you multiply by happens to be negative, you're also going to incur a vertical flip, like we talked about last class. On the other side, and so again, this is where the horizontal things are slightly counterintuitive. If you multiply by a number b on the inside, you're going to affect it horizontally. But here's the thing. If you multiply it by a number that's between 0 and 1, that's what's going to stretch out the function horizontally. Whereas if you multiply by a number that's larger than 1, you're going to squash it horizontally or compress it horizontally. And the reason for that I think about is if you multiply by a number that's big, x has to get smaller to compensate that, so you still end up getting the same y values out. Whereas if you multiply by a number that's small, x has to be larger so that you're still inputting the same thing to the function and getting the same y values out. And I'll definitely kind of show you some examples of that as we go along. And then also, like there, here, if you happen to multiply by a negative constant, that's going to have the effect of flipping it horizontally. Just like multiplying on the outside by a negative constant has the effect of flipping it vertically. So those are the rules of the day. And really that's, I mean, we're just going to take those rules and then kind of combine all the things together. So we're going to talk about what you get when you have a shift and a flip and a stretch all in one. So let's graph some things. And I'm going to try and do the graphs that are on the notes. I'm also going to maybe throw in a few extras. So, and yeah, so here's what I'm thinking about. I want to graph f of x equal to 3 times the absolute value of x minus 4. I don't really so much care about the minus 4 part, although it is going to shift it down 4. I really kind of care about the 3 times absolute value of x part. And I want to show you kind of how that works. So normally I would just kind of graph this, meaning I say like, okay, it's an absolute value. The times it by 3 is going to stretch it up, so it's going to kind of get narrower. Minus 4 is going to shift it down. And we could kind of draw that. We could say, okay, it's going to start off like this, absolute value of x. Hopefully you guys can see that okay. And then multiplying by 3 is going to give us something steeper, like that. And we're pulling these points up. And then finally, subtracting 4 is going to shift that down 4. So at the end, it's going to look like that. And that's fine to have a good idea of what things are going to look like eventually. But really, what I would kind of like to do first is plot some points. And I want to kind of show you what happens. And I think it's going to make it easier to understand kind of why this is a vertical stretch. So I'm going to do x, I'm going to do the absolute value of x, and I'm going to do 3 times the absolute value of x. I'm going to pick some usual values for x, like -2, -1, 0, 1, and 2. Absolute value of these is 2, 1, 0, 1, 2. So if I just take the absolute value of each of these numbers, right, when I plug in -2, -1, 0, 1, and 2, I get the corresponding positive values 2, 1, 0, 1, and 2. But if I multiply those by 3, all my y values are going to be 3 times as large as they were. 6, 3, 0, 3, 6. So I'm taking this absolute value graph that has like the points, 1, 1, and 2, 2, and -1, 1, and -2, 2. And each of those is getting through, oops, and it's right all over my hand. Yeah. Love writing all over my hand. I really hate it. It's the worst. Each of these is going to get 3 larger. So instead of getting 1, 1, I'm going to get 1, 3. Instead of getting 2, 2, I'm going to get 2, 6. And so each of these points is getting pulled upwards by a factor of 3. Or I should really say stretched upwards by a factor of 3. And the same thing on the left. Each of these points is becoming 3 times as large as there. Even this point, the origin, the 0 value is becoming 3 times as large as it was, which is still the 0 value. And then you would just shift that down by 4. So that the final graph, in fact, I just erased something that I said I didn't want to erase. Which I'll draw in a different color just to distinguish it here. The final graph would be shifted down 4. So I'd have, it look like this. It would look like, sorry, it's hard to draw these so they look good. Also, I will point out Desmos is your friend. It's a useful tool all the time. So that green graph will be the final result. 3 times the opposite value of x minus 4. Let's look at some more examples. In fact, so actually I really want to kind of stress the importance of the next example. I'm definitely going to show you some values for this one. I might even do 2 examples here. So let's look at, I want to graph, yeah, I do have 2 examples on my notes here. So I want to graph f of x equal to the square root of, I'm going to say 1/4 times x. And so just from what I said, just erased here back, right? We know that multiplying the inside of the function, or I should say, really multiplying x by a number before you do the function, right? If I was doing this instead, 1/4 times the square root of x, I would see this as, oh, I take the square root of x and then I multiply by 1/4. Whereas here, first I'm multiplying x by 1/4, so I'm kind of doing it before I apply the square root part of the function, and then I take the square root after. So here I'm multiplying before I do the function, or inside the function. And so I know that since 1/4 is less than 1, that's going to be a horizontal stretch. And here's why. So if we were just graphing the regular square root function, x, square root of x, these would be the points we would usually pick. We usually pick the nice square number points for x, like 0, 1, 4, 9, 6. I mean, not that you can't pick other points. These are the ones that have nice y values. And I really should say this is, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. You can obviously plug in like 2, square root of 2 is about 1.4, square root of 3 is about 1.73, and so on and so on and so on. Okay, but now I want to point out, because it really is different. Now, instead of trying to graph or plot points for the square root of x, I'm plotting points for the square root of 1/4 x. And here's the thing. Although we are certainly able to pick any points for x we want as long as we're in the domain, so here x has to be greater than or equal to 0, we're going to try and pick points that are easy. So I want to still pick points that are easy to take the square root of. Like, I want 1/4 x to be 0 because the square root of 0 is still 0. And I want 1/4 x to be 1 because the square root of 1 is 1. And I want 1/4 x to be the next one, which is 4, because the square root of 4 is 2. So I want 1/4 x, the thing I'm taking the square root of, to be nice. Here's the thing. 1/4 x isn't x. X has to be 4 times as big as 1/4 x, because literally x is 4 times as big as 1/4 x. So if 1/4 x is 0, x also has to be 0. If 1/4 x, right, if 1/4 x equals 1, multiply both sides by 4, x equals 4. If 1/4 x is 4, multiply both sides by 4, x equals 16. If 1/4 x is 9, x has to be 4 times as big, it has to be 36. And so on. So I really, really, really want to stress this. Whoops. Here, if I was graphing the original parent function, which I will graph, the x values are what they usually are. But for this function here, if I'm graphing the x values and the y values, right, the x values are 4 times as big as they are here to get the same y values as we have over here. And that's why we're getting a horizontal stretch, because to get the same heights of the function, you're stretching out the x values way to the right. So here's what this looks like. I'm going to try and graph it nicely. Also, I'll probably show you on Desmos as well, because I think it's worth looking at. So here's my parent graph in black, 0.0011, 4, 2, and maybe 5, 6, 7, 8, 9, 3. And again, it's not going to be perfect because, you know, I'm a human being most of the time. Okay, it looks kind of like that. And then what's going to happen is, for the graph of the square root of 1/4 x, I'm going to get 0, 0, so it's still the origin. And then I'm going to get the point 4, 1. So 1, 2, 3, 4, 1. And so look, the point 1, 1 got stretched out over there to the point 4, 1. And then instead of, so I didn't even have, right, 16, 2 is a little too big, right? And then I don't have enough room here. But at this point, 4, 2, we get stretched way out to 16, 2. So this graph looks kind of silly, but it's going to be like, right, it's going to be, right, I'm just stretching these points to the right. And let me show you on Desmos, because I think it's nice to look at. So, share my screen. Yeah, share my screen. Sure. Let me share a thing. Also, please chime in if you have questions. Certainly okay if you don't, but you're always welcome to ask things. So if we graph y equal to the square root of x, looks like that. And we don't really care about the left side here, so let's just scooch this over. And then here's the thing we just graphed, y equal to square root of 1/4 x. So you can see that, oh yeah, look, this point here, 1, 1, right about there, right? We can go over to the right and be like, oh yeah, there's the point 4, 1. So it stretched it way out. But we could also smush it. We can compress it by multiplying on the inside by a number that is larger than 1, like let's say 9. So y equal to the square root of 9x. So look at that. Here you can think about, oh, this 0.11 is getting shifted way to the left. It's going to be 1/9 as big. And let's see if I can get it there. So maybe it's hard to, it's hard to get that point. Let me try and zoom in a little. So that point there is the point. So I can't actually get there, but it is the point 1/9, 1 is the point I'm trying to look for. I know there's a way to do this here, but I don't remember what it is exactly. Maybe I can use it. Let me try something. No, they don't want to do it. Okay, fine. But right, this point here is going over there, and all these points are compressing to the left. Now, I will say, because this is a common observation that people make. That horizontal compression of y equal to 9x sure looks a lot like a vertical stretch. And it is in this case. That horizontal compression by a factor of 9 is equivalent to a vertical stretch by a factor of 3. Right? Same graph. Green graph, purple graph. Same graph. So, especially if your graph goes through the origin, a vertical stretch and a horizontal compression can look the same. Just like a vertical compression and a horizontal stretch can look the same. They're not always the same, but they often have a very similar effect. Okay, let's do some more examples. In fact, before we do more examples, though, I want to talk about putting it all together. So I just got really loud in my house because there's some vacuuming happening. Hopefully you guys can't hear that, but yeah, I sure can. So, I was like, we have you muted, James. We can't hear anything. Just kidding. I don't think we have me muted. I think it's just that I do a lot of talking and you guys are like, yeah, taking in the information. So generally have this kind of setup. If you have y equal to a times f of, oh, something's happened. I don't know why my computer likes to flip out sometimes. Sorry. B times x plus c plus d. So these are kind of all the things you can do to a function. And I really, really, really think it is worth your while when you see this kind of gobbledygook, and we'll write an example down in a second, to work from the inside out, if that makes any sense. So I'm gonna write let me be consistent here. I'm gonna do I forget what colors they used. I think they used red. I'm gonna do the horizontal things in blue and the vertical things in red. And so the horizontal things happen inside the function. So right here, adding c, this is going to shift left or right. It's a horizontal shift. And it's a shift to the left if c is greater than 0, a shift to the right if c is less than 0. I should, whoa. No, that's right, sorry. I'm thinking of something else. Yeah, that's totally right. I was like, no, perfectly fine. And this b here, right, this is what we just talked about. Multiply by this is going to be a stretch, a horizontal stretch if that number is if that number is smaller than 1. And it's easy to get the horizontal ones backwards. The horizontal ones are kind of counterintuitive. We think making stretches something else making it bigger, and we're having to make this bigger to compensate for this being smaller. So the stretch, if that's between 0 and 1, it's a compression if that number is larger than 1. And then we have the vertical stuff on the outside. So this here, right, it's a vertical stretch if a is greater than 1. It's a vertical compression if a is between 0 and 1. And finally, over here, if you add something on or subtract something off at the end, it's a vertical shift. It's a vertical shift. It's going to be up if that number is positive, down if that number is negative. So let's look at a seemingly complicated example. Oh, and then there's one more thing to say here. If a is negative, that's going to give us a vertical flip, or vertical reflection is the more mathy word. And if a is positive, if B is negative, that's going to give us a horizontal flip or a horizontal reflection. So these are kind of all the ways we can transform a parent graph, right? If you start out with some parent graph, you can do all these things. You can shift it up, down, left, right. You can stretch it out horizontally, smush it in horizontally, stretch it out vertically, smush it in vertically. You can also flip it vertically or flip it horizontally. Those are kind of all the things you can do. So let's look at an example. Also, just as an aside, I want to remind everyone to vote. I voted yesterday, got off my ballot, got a text message from the county saying that my ballot was accepted and will be counted. So if you're able to vote in this country and you're of age, please vote. It is important. It's a right. We should exercise it. So yeah, vote, 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 vote. Also vote. Okay, enough of the voting. Back to the math. So let's look at this example. Let's look at y equal to negative square root of 2x plus 3. And so again, here's what I want you to think about when you see this. I want you to really think about working from the inside out. So this 2 is going to give me a horizontal compression. This negative sign is going to give me, it's outside. So I'm thinking of the function as the square root function. So I'm kind of, you can even think of it this way, right? I'm starting with the square root of x. Then I have the square root of 2x. That's my horizontal compression. Then I'm going to put a negative on the outside, negative square root of 2x. That's also going to give me a vertical flip. I could say this a different way, but I'm going to say this way. And then I'm going to add 3. Which is going to give me a vertical shift up. And I kind of like to, so I can definitely show you these graphs that I've graphed in the notes. I could draw it for you. I don't feel like me drawing it for you really shows you anything specifically amazing, although I can certainly do that if you guys want me to. But let me Desmos it up for you, and then we can talk about how we might do this. So here's the way I'm kind of thinking of it. So I'm really kind of thinking of these steps. I'm thinking first, parent function. Square root of x. Great. Then I'm thinking of the horizontal compression. So look, that moved it, or I should say it scrunched it inwards to the left. I wish there was a way I could, no, I can't really do that. Yeah. And then we're going to do the vertical flip. So we're going to put a minus sign on the other side. So that took the blue graph and flipped it over. We can even get rid of these older ones if we will. Oops, I didn't want to do that. I want to do that. Sorry. And then finally, we're going to take that one and we're going to add 3. So we're going to shift it up by 3. I can just, you know what, copying and pasting is really a great thing to do. There we go. Awesome. And then add 3. And that shifts the whole thing up by 3. So we can see, oh yeah, there's the final result. If I was graphing this, without using Desmos, I probably don't want to graph all the graphs. We certainly can, but we don't have to. What I might do is think about what's going to happen. So I'm like, okay, I can see that my original graph of the square root of x is going to get smushed in, flipped over, and moved up 3. So I know it's going to end up looking kind of like I'm going to be up 3. I really do think about where kind of the important origin point goes if you have the origin. When I smush it in, it stays where it is. When I flip it over, it stays where it is. But when I move it up 3, it moves up here. So I'm going to do something like something like this. And I mean, that's kind of good enough. I feel like we could plot some points if we really wanted to, right? We could try and pick some easy values of x, but that's not really the point. Like you could pick x equal to 0, you get y equal to 3. You could pick, so here I have to be a little careful. Like if I want to take the square root of 1, I kind of have to let x equal 1/2. And if x is 1/2, I get the square root of 1, which is 1, minus 1 plus 3 is 2. So I plug in 1/2, I get 2. And then the next value I pick would probably be 2. Because when I plug in 2, 2 times 2 is 4. The square root of 4 is 2. Negative 2 plus 3 is 1. And so on. And I just kind of happen to luckily graph it so it looks kind of right. Also, I was looking at the graph that I already had in Desmos. Let's do some more. Again, stop me if you've got questions. There was something I had to say. Now I'm not remembering. I guess, sorry, next example. Where'd you go, examples? Okay, let's look at this next one. Okay, so again, I'm working from the inside out. So let's try and graph f of x. It's a -1 over x minus 4 squared. Or if you prefer, and you might prefer, to make it a little easier to see, you might think of it as -1 over x minus 4 squared. So when I look at this -1 over x minus 4 squared, I'm thinking that my parent graph, my parent function, is 1 over x squared, which we know looks like this. I know it was like the last thing we did in class on Monday, but that's the basic idea of the graph. It looks like that. And the points I used to think about having are the points 1, 1, and the points -1, 1. And it has a vertical asymptote at 0, meaning as we get closer and closer to 0 from either side, in this particular case, the function gets infinitely large. Okay, so then the first thing we're going to do is what? So there's two things happening here. There's some sort of shift and there's some sort of flip. And although we could probably do them in either order, if you're me and you're working from the inside out, do I want to do the shift first or the flip first?
Shift?
Yeah, I want to do the shift. Specifically, the horizontal shift. So I will say, if I had a vertical flip, a vertical shift at the end, I would probably do that last. And I know I talked about this last time, but there is an order that I think we should do things in each time. And the order is first, sorry, I have to remember, horizontal shift, horizontal flip, vertical flip, vertical shift. This is the order that is safest to use to do things in. And the stretching kind of goes along with the shifting. So if you happen to have a stretch that happens at the same time, you would do a flip as well, because it kind of comes from the same coefficient part. Here we don't have that, so it's not a worry, but I just want to make sure. So I should really say, first you do a horizontal shift, then you do any horizontal flipping or stretching, then you do any vertical flipping or stretching, and then you do any vertical shifting. But yes, horizontal shift comes first. So we're going to shift this forward to the which way? Are we going right or are we going left?
Right.
Yeah, right, because x has to be 4 larger than it was before to get the same things to happen for y. You can also think about how this one has a vertical asymptote at 0, This one's going to have a vertical asymptote when x is 4 because the denominator will be 4 minus 4, which is 0, which is undefined. So here's my vertical shift, my horizontal shift. So now instead of getting the point 1, 1 and negative 1, 1, I'm going to get the point that's 4 larger for the x value. So I'm going to get the point 5, 1 and 3, 1. It's going to look like this. But I'm not done, right? This is 1 over x squared. This here is positive 1 over x minus 4 squared. And then the negative out front, the negative outside of the function is going to give me a vertical flip. So I'm going to take this whole graph and reflect it across the x-axis. So my final result, which I'm going to erase here and draw. I'm going to take that. I should point out, my expectation is not that you draw every intermediate step. I am drawing every intermediate step to show you guys the thought process behind how you get to the end. But really, if I was graphing this like as a homework assignment or as a test question, I wouldn't be doing all these individual intermediate graphs. I would be trying to just graph the final results. The final result, right, I've shifted my parent graph 4 to the right, and then I'm going to flip it over. So this point that was starting at 1, 1 moved over to 5, 1, and now it's going to flip over to be 5, negative 1. And similarly, this point that was negative 1, 1 became 3, 1 is going to now be 3, negative 1. It's going to look like this. Oh, sorry, that's a positive. Sorry, ooh, I labeled those wrong. That's a 5, negative 1, and that's a 3, negative 1. And when I graph these shifted, stretched, transformed functions, I often think about how some of the more noticeable points end up changing. Like for my square root functions, I think about, well, usually a parent function, square root function, starts at 0, 0. I think about where that 0, 0 point moves to. This function doesn't have a 0, 0, so I take the next best thing, which is a 1, 1, and I think about where that ends up moving to. And that is often my kind of plan of attack for seeing how a function looks. So let me try and do this next one without doing all the things. Meaning I'm going to try and just graph the result. We'll see if I can actually make myself do it. So here's the function I want to graph. Maybe I'll do it and then I'll kind of show it on Desmos. So I want to graph f of x equal to the absolute value of 1/3 x minus 1. Oh yeah, this one has an extra trickiness. Minus 4. Okay. So I did say we should do a horizontal shift first, and that is true. And I want to warn everybody, in this example, the horizontal shift is not positive 1. It might look like it's positive 1, but the problem is there's also this stretch. And the stretch and the shift together mean we have to be a little extra careful. I need to rewrite this. So there's actually 2 ways of tackling this. One way is to rewrite it. I can totally rewrite this as the absolute value of factor out a 1/3 from here. If factor out a 1/3, I'm left with x minus what? X minus 3, right? Because I divided by 1/3, and divided by 1/3 is like multiplying by 3. So now this way you can see, oh, my horizontal shift is 3 to the right. Here's another way to see that. So typically, we think about an absolute value function as having kind of like its vertex, actually, it's literally what we call it. The bottom of the V for the absolute value function is kind of where you think about the function starting. So normally, the bottom of the V is when the insides are 0, right? Because 0 is the smallest an absolute value can be. So normally for an absolute value function, you say, okay, well, the bottom of it is at the origin, because when x is 0, that's as small as this can be. So the idea is to say, well, what's going to make this whole inside equal to 0? So you can say, well, I'm going to set the inside equal to 0. 1/3 x minus 1 equals 0. 1/3 x equals positive 1 times by 3, x equals 3. So that's another way you can figure out the horizontal shift. If you would normally start with x equal to 0, where the x is what's inside the function, you can say, I'm going to set all the inside stuff equal to 0 and see what you get. It's not foolproof, but it's definitely something I'm going to come back to when we start talking about graphing sine and cosine and how the horizontal shifts and stretches work there as well. So yeah, this one we have a horizontal shift to the right. We have a horizontal stretch by a factor of 3. Which means all of the x values are going to be 3 times as large as they would have been. And then we're going to shift down 4. Now the hard part is, how precise do you really want to be? I want to not have my board move all over the place. That's what I really want to happen. So here's what I know. I know it's going to move to the right, and I know it's going to be not as V-like. It's going to be more wider out because I'm having a stretch out, right? All the points are moving outward. So I know I moved over 3. So instead of having the point 0, 0, I have the point 3, 0. So it would have been like that. Then I stretched it out so it's more like flatter kind of, and then I moved it down 4. So the vertex, which is what I'm really thinking about, is down here at the point 3, negative 4. And we can see that if I plug in 3 for x, I get 0 here, here or here, and then 0 minus 4 is negative 4. And then it's going to go up like that. Now, one way you could easily figure out how to graph it is just to see what the y-intercept is. If you plug in 0 for x, 1/3 times 0 is 0, minus 1 is minus 1. Opposite side minus 1 is 1. 1 minus 4 is negative 3. So you can totally see like, oh, well, my y-intercept is going to be 0, negative 3. So it's going to go through that point right there. And it's going to look like that. Oops, wow, I can't even graph it. Come on. And then same kind of deal to the right like that. Eventually there would be an x-intercept. We could totally find the x-intercept by setting this equal to 0. If you set this equal to 0, then the absolute value of 1/3 x minus 1 has to equal 4, which means the insides either have to be positive 4 or negative 4. So you get 1/3 x minus 1 equals 4, which is 1/3 x equal to 5, which is x equal to 15, or 1/3 x minus 1 equals negative 4, which is 1/3 x equal to negative 4 plus 1 is negative 3, which is x equal to negative 9. So you have an x-intercept over there and an x-intercept way over there. I'm not saying you have to find the intercept. I'm just saying these are some of the tools I use to graph things like this. I kind of think about, well, I know what the stretching is going to do. What's that going to leave me with? I feel like I have... No, I guess not. So there's one more on the notes that I think is fine. It's just taking 1/2 x minus 2 cubed. I don't find that particularly. I think you can look at that one in the notes on your own. Oh, I know. I was going to show you one. I was going to go back to Desmos for a second. I'm going to show you what I think of this one. I want to do a different one though after this. So let me show you on Desmos real quick. Like, this could I think again. I really do, especially in this kind of online world that we are all living in for the near future, I think it is worthwhile for you all to get comfortable utilizing this tool because it's a powerful tool and it is one your teachers will often refer to. So we were doing the absolute value of x. And then I'm thinking about doing the shift first. So I'm saying, okay, well, I said it shifted 3 to the right. So I've got y equal to the absolute value. Absolute value is what those x minus 3. So that shifts it 3 to the right. And then we're going to stretch that by a factor of 1/3 by a factor of 3. So multiplying the inside by 1/3. Right, so right, you have to do the horizontal shifting before you do the stretching, which is why I had to kind of factor that 1/3 out. So you get y equal to the absolute value of 1/3 times x minus 1. Sorry, x minus 3. Right, so I've taken this shifted graph to the right and I've stretched it out by a factor of 3. And then finally, we're going to shift it down by 4. Let's do copy paste. Let's be smart. Let's be efficient. So same graph, just every point's moved down 4. It's not too terrible. Okay, let me throw another example your way. So I do encourage you to look at the last example in these class K notes, but I want to do a different example for you because I'll show you one more. So let's look at, I really like the square root function because it doesn't have any symmetry, unlike some of our other functions, which usually have some sort of symmetry. Maybe not though, maybe I'm a liar. Let's look, yeah. So let's look at this one. Let's look at y equal to, had something that went away. Yeah, let's look at this. Let's look at y equal to 3 times x minus 1 squared. Not really all I want. Minus 2. Yeah, it is because there's something I want to show you. So this is going to have, so this is going to shift us right 1. We're going to stretch vertically by a factor of 3. And we're going to shift down 2. And the thing I want to say is, the thing I want to point out, well, in fact, we can draw this, right? So we're going to go over 1. So right, usually a parabola would be the usual, right? This is the parent graph, I should say, would be the parabola y equals x squared. We're going to go over 1. Then we're going to stretch by a factor of 3. So over 1 would be like the usual parabola looking like this. But then we're going to stretch it up by a factor of 3. So we're going to look kind of more like, different colors are good. Look more like this. And then we're going to shift that down 2, which is going to end this up right there. And the thing I want to point out is here, this stretching by a factor of 3 isn't quite the same as compressing by some other thing because we also have some shifting that is affecting things. So that's kind of the point I wanted to make, was that before I said, well, sometimes it's a vertical stretch and a horizontal compression are interchangeable, but only really in special cases. Most of the time it's just be like, oh yeah, they're completely kind of different. I suppose I should finish this one. So I know that I'm going to go down 2. So my end result here would be a parabola whose vertex is at 1, -2. Right? If you plug in 1 for x, you get -2 for y. And is much steeper looking than the usual parabola. Like that. There are some there's a y-intercept and some x-intercepts we could find if that was what we were being asked to do. But I probably wouldn't unless I was being asked to. These graphing questions are mostly just asking you to talk about how the thing is being transformed. Let me do, yeah, I got time. Let me give you one more. So let's say we have f of of x equal to the square root of negative 2x plus 4 plus 3. All right. Horizontal shift. Left or right? Yeah, I'm not sure either. Like, it is left. So I'm just thinking, but so here's the thing. It's not left by 4. Because I have to factor out the 2. So really, I've got f of x equal to 2 times negative x plus 2. It's really a shift left of 2. So here's what I'm kind of thinking of this. And this is, yeah, I'm going to do it this way. So I'm going to draw the things. So here's my shift left 2. So I know it's right, square root of x plus 2 shifts it left 2. Okay. Then I'm going to throw in the negative. The negative is going to give me a horizontal flip. So horizontal flip, square root of negative x plus 2. So that's going to flip this whole thing across the y-axis, which looks like this. And some people like to imagine this first, that we kind of did a shift to the right and then flipped kind of around this point. That's also a way you can think of it, but I feel like it's more consistent to do the shift first and then to think of flipping this way. But it does, in some sense, kind of look like, oh, well, we really ended up moving to the right. Because first we moved to the left, and then we flipped it around like that. And then we're going to have a horizontal compression by a factor of 2. Well, not actually by a factor of the square root of 2, really. Because it's inside. Inside the function is always a little wonky. So, well, no, I lied. That's, yeah. X has to be half as big as it was before. So when you're compressing by a factor of 2, everything moves closer to the vertical axis. So instead of getting the point 2, 0, that's going to get closer to the x-axis by a factor of a half, or by a factor of 2, whichever way you want to say it. So I'm actually going to get the point. Oh, I could be wrong. I could be totally wrong. Now I'm like, that's funky. I don't know if I love this one, I gotta say. Yeah, I should be having a horizontal compression, but I'm still getting this point here. This is still a point. Sometimes these problems are kind of weird. Sometimes you just have to kind of work them out step by step. So we are getting horizontal compression, but I guess we're compressing more towards here, which isn't always what's going to happen. But horizontal shifting and flipping can always be dicey. So what I'm really trying to say is be careful. But if we look at this, right, the x values are going to be half as large as they were. So like, for example, here if x is 0, we get the square root of 2. Here if x is 0, we get the square root of 4. Here if x is, say, like, I think the problem is that there's a shift that's also happening. Yeah, I see the problem. It's more that this has to be half as big as it was before. I see. Sorry about that. So here's the real issue. This quantity, negative x plus 2, has to be half as big as it was before. So if this is 0, well, half of 0 is still 0. So if this was equal to, say, if this was equal to, say, 2, when x is 0, so this part is equal to 2 when x is 0. This part has to end up equaling 4 to get the same result, right? Because it has to, this part has to be half as big as that part. And I feel like I'm kind of getting in the weeds a little bit here, but I think this will make it a little bit clearer. So for this to be 4, x has to be negative 2. So at negative 2, square root of negative 2 plus 2 is 2 plus 2, which is 4. I get the y value of 2. So this value has been smushed that way, right? Whereas here we get 0, 2 instead of negative 2, 2. which I know I've drawn them kind of virtually the same because my drawing isn't great. One note about this, and I'll let you go since it's 201, 202, sorry. I wouldn't worry too much about the horizontal flips and the horizontal stretches. I don't think I asked many questions about that, but I do want to let you know that the name of the game here is really to be careful, use the tools you have at your disposal. I think it's definitely worthwhile to look at each of the steps through Desmos and kind of see like, okay, what does each step through the transformations of this graph look like? And I will end there because